Thank you very much. So, I'm going to talk about distortion today. It's my third time in ADC, and it's really a pleasure for me to be here again this year. And I'm again doing a talk about virtual analog modeling, but this time I'm going to try to be more practical about how we can make amazing distortion audio effects. I will show you how to add some analog warmth to all the methods you already know to make a distortion audio effects. And as you may all know, I am kind of a distortion fanatic. I did a PhD thesis about guitar amplifier simulation. And to me, distortion is one of the most interesting audio effect to study because it can take a lot of different shapes, and because it is everywhere, anywhere. Every single time you're trying to copy the sound signature of something from the analog world. And the whole virtual analog stuff is basically at more than 50% related with distortion. And I am also an electric guitar player, and distortion is probably the most important recipe in most of the signature guitar sounds. Evolutions on ways to make the guitar sound more distorted have literally changed the whole music world. They have literally pushed the creativity in music. They have created new kinds of music, new style, labels, providing new ways for musicians to express themselves. And that's why you will have a hard time finding guitar amplifier in a shop which don't provide saturated channels. And even in electronic music, distortion is everywhere. It is a creative effect, you know well in the guitar context, but also a component which provides extra warmth, the analog vibe. A lot of people like in compressors, limiters, synthesizer filters, tape recorders, studio consoles, strip channels, and some kind of digital-only inspired distortion can be found in a lot of recordings in some very specific musical styles in electronics. And as we will see soon, the word distortion has also a lot of different definitions. And the term nonlinear in general is something that we can see not only for amplitude-based distortion, but also for very interesting stuff that we'll see just after. So, I'm going to talk about distortion effect using some category labels. So I will start with static waveshapers. And by the way, I have to tell you that when the talk will be finished and when I will be back in France after the ADC, I will create a topic on the Juice forum, and I will put a lot of content related with the talk on it. You will be able to download all the source code examples. I will also give you some homework to do, so you will be able to play with some of the concepts you will have seen, and you will be able to ask all the questions you need to complete the homeworks. And I will also give you a Juice project for a waveshaper distortion algorithm with a lot of things inside. And I will post a PDF file with all the explanations about all the concepts we will see now during the talk. So, we're going to start with static waveshapers. And the static waveshaper class is basically just something like that. So it is a simple analog processing block scheme showing you what we are doing to the sound. So basically we just take the input, we apply a function to it, which could be linear or nonlinear, and we get our output, and that's all. All the static waveshaper algorithms that we will see first are just that thing. And I think the most simple and the most used algorithm in this class is what we could call the hard clipper. That's basically something that we use a lot in limiters and in plugins in general to prevent the ears from the musician to disappear because of something they did. And in limiters, even if we do a lot of very complicated stuff everywhere to be able to increase the loudness and having a whole mix sounding very good. At the end, very often we add that thing to be sure that at the end everything is properly limited below a given threshold. So this function is very simple. It's just doing nothing to your input, just returning the output until the amplitude is higher than a given threshold. And then you limit in a very hard way the output of the function. And you could use that also with some input gain control just before to create some nasty distortion. Because as you can see, the knee between the linear and the nonlinear side is very hard. So it is called a hard clipper. And it can add a lot of harmonics to any overdriven signal. And then we have other waveshapers that we could call softer clippers or sigmoids. It's all the time some functions that have a S kind of shape curve, and you can use a lot of very different functions to get a curve like this. And for example, if you want to use a hyperbolic tangent, which is one of the sigmoid waveshapers we use the most, you can just do something like that in terms of code. And you can use that the same way than the hard clipper to prevent your outputs to be higher than a given output amplitude. But it is something that we use a lot to do some standard distortion audio effects. And you can find on the internet, for example, on the Music DSP or Archive website, a lot of different waveshapers. During the beginning of the century, a lot of DSP engineers were trying to find the holy grail of the sigmoid waveshaper. They were all trying different functions to get something that sounds good, that is not too CPU hungry. But at the end, it's always almost the same thing. And if we want something more interesting in terms of sound, we will need something else, but we will see just after. This is the strongest waveshaper we could find. That's basically something that makes ugly everything you put through, or very interesting depending on the context. But it can be very funny to use that waveshaper. And a little word about what I call fast approximations of function. For example, if you use a hyperbolic tangent, it's a function which has a cost in terms of CPU loads. And when you use a lot of them in an algorithm, you might want to use equivalent functions that are faster to compute. And that's something I do a lot in my distortion algorithms. And this is also the reason Jolt and me, with other reasons, we developed the DSP module functions classes fast math approximation and lookup tables. Basically, instead of having something CPU hungry, you have something with a little less accuracy, but which can be computed very quickly by your CPU. And the example I displayed for the lookup table is one we get with only 6 points in the lookup table, but you can do something with 100 points to get as much accuracy as you want, and it's not going to be a problem in terms of CPU if you do something like that. So it was just to display you how it looks like. But even if you use something like that with only 6 points, it might be interesting as a waveshaper, why not? And as I said before, the most interesting thing you could do with a static waveshaper is put a gain control in front of it and play with it. And you can get a lot of different tones just with that, without adding anything else yet. And that's something you should do anytime you are experimenting with static waveshapers. And we have some very cool waveshapers that are not sigmoid that I call foldovers algorithms. It's because basically the transfer function isn't increasing or decreasing all the time. It could loop like here with the sine waveshaper. And it is very interesting to feed this kind of waveshapers with oscillators from synthesizer. Something very clean like a sine put here will generate a lot of harmonics. And if you play with the drive control, the way the harmonics are generated is going to change a lot, really a lot. So it's something that is very interesting to experiment with, having your drive control and the foldover. And you can also do things like that if you add the dry version of the signal and get something which is not bounded anymore. So if you put a lot of drive there, you need to have something else after to limit the final output of your signal. And I could talk for hours about static waveshapers, because even if they are very simple and you can get very, very interesting sounds from them in comparison to other methods, it's very often the basic elementary stage that you have to use in your more complex distortion algorithms. So it's interesting anyway to experiment a lot with them. And so we have here other examples of static waveshapers. You have all the class of non-bounded waveshaper, like the one just here. And as I said before, you have to limit your output amplitude at the end if you want to use it. We have rectifier or asymmetrical waveshapers that can be very useful in some given context. If you play with power series and what we call Chebyshev waveshaping, basically you can have a control on the harmonics you generate with a waveshaper. Instead of having an unlimited number of harmonics, you can have only a second order or third order harmonics in your algorithm. And it's quite interesting to add some extra warmth without making it sound like distortion. Because even if my talk is called 50 Shades of Distortions, sometimes what we do want is something which adds just some extra warmth and which is more or less transparent, not all the time heavy saturation. And in the static waveshapers, we have also all the fractions of given function of polynomials. And my fast math approximation functions are basically a fraction of polynomials, by the way. You can use randomness to generate the shape of your waveshaper curves to get some interesting results. And the first homework for you guys will be to create what I call a customizable shape or parametric waveshaper. The idea will be to be able to control the shape of the waveshaper using extra arguments. So instead of having just one argument, which is the input, you will have, for example, an argument called ni, and using Bezier curves, you would be able to make it hard or soft, depending on what you want to do. You could make it asymmetrical if you want. And this specific tool is very useful when we make distortion algorithm. And we are going to see why just after. So I will tell you that again on the Juice forum, but customizable shape and parametric waveshapers are one of the most useful waveshapers in the world to do a lot of stuff. And then the next part will be about playing with filters. So the obvious way to improve the sound we could get from a static waveshaper is just putting a filter before the waveshaper and a filter after. And depending on what you do, you can get a lot of very, very different tones. And here is a list of tricks you can use to play with this idea. One of the most interesting things we do, basically, with waveshapers is having a high-pass filter before to remove some mud we could get from distortion, and having a low-pass filter after to prevent the result from being too much harsh, you know. But there is something even better that we can do, which is called Preemphasis. Basically, the idea is to shape the way the waveshaper is distorting the signal by removing or adding some frequency content. So let's say we use, for example, a shell filter. We remove some low-pass frequency content, we do the waveshaper, and then we do the exact inverse of the operations we do before. So we add the low frequency content we have removed before to compensate what we did on the linear side. But doing so will still generate a distortion which has given characteristics. So, for example, if we remove first the low frequencies and then add them back, we get something which sounds like an overdrive and which is very interesting to use on the guitar sounds. And if we do the contrary, we get something very, very muddy, and it sounds like fuzz guitar pedals. And that's something you should really try to do by yourself, and you will be able to do so with the plugin I will provide on the Juice forum. And the tone controls we see very often as distortion pedals are basically a control that gives you a combination of low pass and high pass filtering. Low pass can also be used as a cheap speaker cabinet emulation, which is quite useful when you play with guitar sounds. For example, one of the most known overdrive pedal, which is the Tube Screamer, is basically a distortion unit with a high-pass filter around 700 Hertz, just before the distortion, something like that. And this is how you get the typical sound of that Tube Screamer, even if we do more or less extensive and complicated things on the distortion side after the filter. And you can get as well extreme results by playing with high-pass and low-pass filter with extreme cutoff frequencies. And the structure we have just seen could be used as an elementary DSP block, the word structure with pre-filtering, waveshaper, post-filtering. And this block could be used in a lot of different ways. You could cascade several of these blocks in serial and make something that sounds like a guitar amplifier simulation. I know that a few commercial products available on the market in the beginning of the century for guitar amplifier simulation were working like that. You could play with the dry control. You can add the signal without any saturation to the output of your elementary block. You could put some of this block in parallel and change the parameters of each block to get some extra warmth in your signal. And a lot of commercial plugins doing saturation in the digital sense are doing this with multi-band processing. So you could have a waveshaper and filters only for the low frequencies, and then other ones for the high frequencies, etc. But even by adding those filters, we still experience some lack of life in the result. And everything sounds more like the same with the same filter parameters. All the waveshaper will still sound more or less the same in this context. And if we want something different, we need to use other approaches. And now I'm going to talk about dynamics processors. They will give us hints about what to do to our waveshapers to get very different results in terms of distortion audio algorithms. But still, dynamic processors like compressors, limiters, noise gates, transient designers, they are not saturation effects, but they are nonlinear audio effects. And they had a lot of harmonics, not as much as distortion. And so it's still interesting to talk about them in my talk. The interesting thing about dynamics processors is that basically their analog block scheme is this one. We have something which is called a VCA in the electronic world, which means voltage controlled amplifier, which has only one function. It is to apply a gain to your input samples, input voltage, and nothing else. And basically, a compressor is exactly that and nothing else. The interesting part of the compressor and what is going to make it sound good or bad is how we choose this gain to apply. Because this VCA is not applying a constant gain. It is applying a gain which changes with what is happening in the input signal. It's like having a human moving a fader in a console during the processing of the signal, but instead of a human, we have an algorithm which find out which is the right gain to apply. So basically, we have our input sample here, And we have a sidechain signal, which could be the input signal or something else, depending on what you want to do. But here we are going to take the input signal as an example to see what we can do with that. And I'm going to talk specifically about what the compressor is doing. So basically, compression is using a transfer function to determine what gain to apply to our signal. It is the most well-known dynamics processor. It's a classical nonlinear effect. And its goal is to reduce the dynamics or the loudness of a given input signal by attenuating its level when it is higher than a given threshold with a given amount of compression, which is set by a parameter called the ratio parameter. And the trick to create a successful compressor is not to apply that level transfer function directly on the signal to process. If you do so, you will get nothing else than a static waveshaper. So instead, because we want less distortion and something which is more transparent, we will feed this function with the envelope of our input signal, something which is moving slower than the input signal itself. And so the gain changes will be smoother as well, even if they are going to be significant, but they will not generate a lot of distortion. And to do so, we need a tool which is called an envelope follower, which is the combination of a few things. Basically, we have a rectifier, we have what we call a ballistic filter. Oops. A ballistic filter is something that provides some smoothing to any given DC signal thanks to two parameters that we see all the time, which are called attack and release, which are basically time constants. And they say that we should follow the input signal at a given speed when the waveform is rising, that's for the attack, or falling, that's for the release. And by setting the attack and release parameters, like in this example, we can get the red function that is here. And if we smoothen it a little more, we can use it directly as the control voltage signal to tell our VCA how to compress the signal. And this is actually this red signal that is going to be used with the transfer function we saw before. And this is how we do compression. And this is a very basic compression algorithm code that you will be able to download on the JUICE forum. And it is just doing what I just said before and nothing else. And it sounds quite good, just doing something like that, even if you can improve it if you want. I don't see my mouse very often. OK. So I talk about the compressors because it gave us some hints about what to do to improve our waveshapers as well. One day I did a cool experiment, I think, which was developing an audio effect, which is a compressor, but where you can mix the control voltage signal with the input signal itself. And by moving this mix control, your audio effect can go from compression to distortion with all the intermediate states. And it was quite an interesting experiment because it showed me how the transition is made between the two. And it gave me the idea to use envelope followers and LFOs to modulate anything in my standard distortion algorithms. So the next part of the talk is about taking an envelope follower or a LFO output to modulate something in your block scheme, in your processing block scheme. For example, you could modulate the waveshaper curves, thanks to the algorithms you are going to code very soon during your homeworks. And you can also modulate the cutoff frequency of all the filters in the block scheme. You can modulate the resonance. And by doing so, you can already achieve very, very interesting results. And for example, I saw recently a patent about tape recorders modeling. And what they were doing inside was using a low-pass filter, which is modulated on its cutoff frequency by the loudness of the input signal. And so, when the signal starts to saturate, you have this low-pass filter which reduces in an interesting way the output volume of the input samples, and that's how they got something that sounds more or less like tape. And I'm almost sure that a lot of people are using similar concepts to emulate tape in commercial plugins. And now I'm going to talk about some kind of distortions that you can only do in the digital world. But first, I will say a word about oversampling. So now we can do oversampling thanks to the oversampling class in the DSP module, and it's very useful because every time you are creating a nonlinear audio effect, you are also creating potentially something which is called aliasing. In the digital world, we have a theorem which is well known, which is a Nyquist theorem, which tells us that we can have frequency contents higher than half of the sampling rate. But this is something important when you convert an analog signal into a digital signal, but it is also very important when you're generating yourself some harmonics from any given input signal. And in the case of distortion, we are doing that a lot. So what we can see here is what happens if I have a sine put through a waveshaper with a lot of gain, with oversampling and without oversampling. As we can see on the first table, there are a lot of contents everywhere, and the worst part is that all the extra peaks are not related at all with the frequency of my input sine. So that means that they are going to sound unharmonic to their ears, and they are going to sound bad in a lot of cases. And you may like that, but for example, for a guitar effect algorithm, you would like to have something as clean as possible in terms of aliasing. So what we do is that we are processing our signal in higher sampling rates than the current sampling rate of the project. So we are doing this in a way that allows us then to remove all the extra peaks that we can see here. So what we can see in the second and in the third picture is what happens with the same sine in the same waveshaper when we use 2 times oversampling or 4 times oversampling. And then at the end, we filter everything which is after the line in the middle, and we keep only the first part of the picture. So we can see that we don't have a lot of aliasing in the last case. But as I just said, we might want to keep this aliasing for given sound signatures. And this is what is about in the algorithms called bitcrushers. Basically, a bitcrusher is something that makes a creative use of all the audio artifacts we can get from badly done oversampling, undersampling, from badly done quantization. And this is an example of how we can add a lot of digital distortion to a signal by replacing a lot of the samples in the input signal by zeros. Just doing that is the basics of bitcrusher algorithms. We have other examples of distortion-only algorithms, such as what we call slew limiters. And this is a software which is called VCVRAC. You should have a look for that if you don't know it yet. And I studied some of the algorithms that are inside this software, which is open source, and I find out this slew limiter, which is quite interesting, I think. Slew limiting is basically an effect which doesn't allow the waveform shape to move with a given threshold speed. The speed of the shape is basically something which depends on the amplitude and on the frequency of the shape. So what we can see here in this curve is that the amplitude is increasing too quickly, and the slew limiter can't cope up with this speed. So instead of following the curve, it is doing a ramp which is moving at the maximum speed that is allowed. And by doing that, you can change a lot the shape of your waveforms, and it's something which isn't that complicated to code in terms of number of lines, but it's not just a static waveshaper. It's like a waveshaper which depends on the slope of your waveform. It depends on the derivative of the waveform, actually, and it's quite an interesting audio effect. And we can find a lot of other examples of digital-only distortion algorithms, like things you might already know, stuttering, doing some wave shaping stuff in the FFT domain instead of the time domain. We have ring modulators, which are basically a LFO multiplied by your input signal, crossover distortion, binary operation directly on your variables. And it's a lot of fun to play with all these things. But now, if I can move my mouse, we're going to talk about analog modeling distortion, finally. One of the ways to do so, to do analog modeling distortion, is to use an approach which is called Blackbox methods. It's like what we did a lot in the past with impulse responses measurement. In the beginning of the century, a lot of musicians were amazed by the fact that you could simulate something from the analog world just by doing a very simple measurement from it, taking the impulse response, which model the linear part of its behavior, and use it in a convolution processor to simulate with your computer how the system behaves. But it works only for linear systems, unfortunately. So you can only simulate reverberation or a cabinet from a speaker, from guitar amplifiers, if you don't consider the nonlinear part, doing that. And of course, a lot of people were dreaming about doing the same thing with nonlinear systems. So you don't have to know anything about the system, and you could replicate it with a computer if methods like this exist. And they do exist. There is one thing which is called dynamic convolution, which has been patented by a company called CentFX, which basically it's like convolution, but the impulse response change at every sample, depending on the loudness or the amplitude of your signal. And by doing so, you can introduce some nonlinearities, and it is being used to model some compressors in some commercial products. You have also the Volterra series, which is basically the generalization of the convolution operation, but for nonlinear systems. But it's very, very complicated to use because basically you would need to have impulse responses which are three-dimensional or four-dimensional to be able just to model the third harmonic generation of a system. So some people are using it as they do amazing things with that, but you can't do very heavy saturation with it yet, unfortunately. This is some products which use dynamic convolution and Volterra series. But the magical tool that we use all the time to do analog modeling with a white box method, which is when we do know what happens physically in the system, is a method which is called the Newton-Raphson algorithm. Basically, you have an equation that you want to solve that is equals to 0, and you want to know which x which makes this equation equal to 0. Sometimes it's very easy to get. For example, if my equation is x multiplied by x minus 4 equals 0, then we all know that x equals 2. But sometimes you don't know the exact value, or you want to have a numerical approximation that you can't compute by yourself. For example, we could use that to compute an approximation of the square root of 5, and I'm going to show you that. But basically, this algorithm is working iteratively by following what happened in this equation. So we need to know the equation g, we need to know the derivative of the equation g, and then we apply it several times in a row to get more accuracy at each iteration. So this is an example code which is computing a numerical approximation of the square root of 5. And if I use it, I get this result at each iteration. I need to initialize it to 1, and then I compute it once, I get 3, then I get 2.3, then the other values. And with only 6 iterations, we are very, very close from the exact value we could get with the function std square root that we have in C++. But the thing is, this Newton-Raphson algorithm is useful as well to do some interesting stuff in a distortion audio algorithms design. For example, there is a very simple electronic circuit which is called the diode clipper. It's basically a low-pass filter plus 2 diodes. And this is how we draw its analog block scheme. As we can see, we have a very important thing here. We have feedback loops. And this is what makes the difference between our previous algorithms and something that will sound more analog. This is because we have this feedback loop. And because of this feedback loop, if we try to write what is the output depending on the input, we will get some elements related with the output everywhere in the equation inside nonlinear functions, and we won't be able to write an explicit value for our output. So we will need to use Newton-Raphson to be able to compute the result in real time in a given distortion algorithm. And this is a simple low-pass filter. So as we can see, the diode clipper is basically a low-pass filter with an additional nonlinearity put in a feedback loop. And it is interesting to see how we can solve something like that as well, even if it's linear, because it is going to help us to do a lot of things after in the nonlinear side. So this is our low-pass filter in the analog world. Following what we can see in the book, The Art of Virtual Analog Filter Design by Vadim Zavalishin, we can see that it is very useful to just replace the integrator in the analog world with that thing to get the equivalent in the discrete world. But still, we have a feedback loop here that we need to solve to be able to compute the result. So how do we do this? We can do the obvious thing, adding one sample delay in the feedback loop so everything is explicit again, but it will give us a wrong frequency response, and it's not the most interesting thing to do. Or we can solve more or less by hand the equation we get, and we got something explicit because everything is linear, and we can get that thing. That thing is the exact replication of this in the discrete world using the TPT integrator that we can see here, which replaces the analog integrator, and it will give us more or less what we want. But so this is the code for this low-pass filter. But if we want to do the same thing from the diode clipper, even by using this method, we can improve the linear part of the algorithm, but we still need to do something for the nonlinear part. And it's kind of complicated to explain, but this is the code which does the actual simulation of what we see here using Newton-Raphson. And you will be able to have a look to it on the JUICE forum and try to understand everything that is happening here. And one of the homeworks you will have after the first one is doing the same for this. So I will give you instructions to help you recreating an algorithm simulating this structure using Newton-Raphson. And then I will post the solution as well for everybody, so you will be able to play with the algorithms in code. And the thing is, as you have already seen, Newton-Raphson is not something that is all the time very easy to use. And it is also very CPU hungry, because using Newton-Raphson means that you have to make a lot of iterations of the algorithm before being able to returning an output with a good accuracy. And if you have a lot of division or hyperbolic tangents and things like that going on in the iterations, then it's going to be complicated in terms of CPU to have something that is not taking 20% of your CPU and to leave some space for other plugins around. So usually what we do to prevent this from happening is replacing first all the expensive function calls by fast math approximations. And this is where this class really shines, and this is where I use it most of the time myself. You can also add an additional delay in the feedback loop, but that's not something I recommend. Or you can pre-compute all the outputs of the Newton-Raphson algorithm, put them in a lookup table, not to replicate the nonlinear function, but really to replicate what Newton-Raphson is doing. And by doing so, your whole Newton-Raphson calls are replaced by only one use of a lookup table. But the thing is, this lookup table must be filled using Newton-Raphson as well, so everything could work properly. And another method that is being used a lot in commercial plugins is to compute the structure on the linear side, like I did before, and then adding some extra nonlinearities on top of it without trying to solve them using Newton-Raphson. For example, you could just replace all the integrator in the analog world with this kind of integrator, and doing so you will get some very interesting nonlinear effects. You could have a play with this, for example, with the state variable filter structure, which is the one which is in the DSP module state variable filter class. You could just replace all the integrators with the thing we have seen before, and you could get a quite good version of that filter, but with nonlinear stuff going on. And this is a plugin from UH which was very interesting, because when they designed it, they have provided an alpha version of the plugin to the caviar audio community, and you have the possibility to try different versions of the filter modeling engine without knowing exactly what they did. And you have some very cheap in terms of CPU versions, and others which were very CPU expensive. And the developers asked to the users what is the one they liked the most. And it wasn't the Newton-Raphson based, which was the winner. It was another one. It was not accurate, but it was sounding good. So it was quite interesting to see this kind of results in blind tests. And we can do Newton-Raphson on very complicated things. For example, here, this is the Moog filter. Here's the EMS-VCS3 filter. And when we do Newton-Raphson and stuff like that, we need to solve not only one implicit equation at a time, but we need to solve like 2, 3, or 4 implicit equations at the same time. So we have a system of implicit nonlinear equations to solve with Newton-Raphson, which means that we need to use matrices, inversion of matrices, and everything can become quite hungry in terms of CPU. But a lot of people are still doing this using lookup tables to improve things. And in guitar amplifier simulation, for example, we can see a lot of blocks like this, which is basically what happens in a tube amplifier. And it's interesting to see what happened there in the shape of an analog block scheme instead of just equations like I did a lot in the past. So here we can see that we have a block that we recognize, which is a low-pass filter. We have gain additions, and then we have this thing. We don't know exactly what it is. This is, in fact, a static waveshaper, really static, but with 2 inputs and 2 outputs. And this is the shape that these 2 input, 2 outputs waveshaper have, which have been measured on a wheel triodes. And this is quite an interesting block to play with. Okay, so I don't have a lot of time, I think. So I will talk very quickly about other nonlinear phenomena. We know hysteresis, for example. It's when you have a shape for a waveshaper, for example, which changes depending on how you are moving from one place to another. For example, if our input is increasing, we might use this shape, and if it's decreasing, we might use this one instead. And this is creating some nasty sounds, and that's something we see a lot in all the analog stuff related with magnetic, like output transformers, like tape. And that's something we do also with noise gates to prevent some nasty artifacts from happening in some specific cases. We have not amplitude-related nonlinearities. I will talk about them after the talk if you want. We have a lot of nonlinear audio effects happening in acoustics. For example, what makes a wind instrument more brassy when the pressure increases. That's something that can be modeled with acoustic modeling equations, but which could be then used as an audio effect on any given input signal. It's quite interesting to use equations from the acoustic worlds to do audio effects. And we have something that I like a lot, which is what I called glitches. This is like when you do something wrong somewhere in your code. Usually, your Juice plugin crashes and make a Reaper or anything crash, but sometimes it doesn't, but you get something else instead. You have some very nasty sounds not possible to explain, which are released by your plugin. And that's something that happens to me quite a lot when I screw up with the minus signs in my equations. And that's why I always say that the minus sign is my nemesis enemy. Because every time I do something wrong, it is related with this. So I will just finish this talk by making you listen what happens if you feed amplitude 4 with an input sample which is too high and which isn't supposed to be here. So what we will hear is what happens even without feeding it any input after the sample at fault. Okay, I will make you listen to it maybe after. Well, I will do it just after. I think it's because of my jack. My talk is basically finished, so I'm going to do what I need to do to make you listen to this.
Ivan, do you think you can answer questions while you're setting up your...
Yeah, sure.
Okay, any questions? There's one there.
Yeah.
Your work on the Newton-Raphson stuff looks great. I know a lot of people have been looking at it for the opposite and doing linearization of models.
Mm.
Have you explored any explicit methods for calculating stuff? Like in acoustics, we use a lot of basic Euler methods, which do like almost like an oversampling in time.
Mm-hmm.
So that you can, instead of having to do an implicit calculation, you can just recalculate new fields and do partial differentials as opposed to ordinary differentials for solving such things. Have you tried anything like that?
We do have a lot of methods to solve the nonlinearities in time without being CPU hungry instead of Newton-Raphson. So I was talking about the lookup tables. Something we do a lot also is looking at the shape of what is in this lookup table with pre-calculated stuff, and we try to find a function which replicates the shape of what is inside. And we do use also machine learning sometimes to do the same thing. There are a lot of stuff we can do so we are not we don't need to use Newton-Raphson, and a lot of this method is very interesting, and that's tools that people in the nonlinear dynamic system field use a lot in acoustics. We do take some inspiration from all the physics words.
Okay, one more question. Here.
Yes, I have a question. If I remember correctly, Newton-Raphson doesn't always converge. Like, what do you do to prevent this, or what's your?
I have a bibliography part on my talk, which is where there is an article related with this specific issue. Because if you do use only Newton-Raphson to do the whole computing, at some point you will see that if you feed the algorithm with a very high amplitude signal, very often you will get some divergence in the algorithm. So what we usually do to prevent this from happening is oversampling a lot the process, so we can estimate more accurately the solution at the first iteration of the algorithm. And we try to limit the speed at which the delta of the Newton-Raphson algorithm, the difference between the iterations, is increasing. If we see that it is higher than a given limit, we say, okay, the delta is going to be that limit and nothing more. And by doing so, we can make an algorithm converge. And there is a specific article, in fact, which was published during DAFX, I think it was the 15th, which is related with this and which talks about all the issues related with Newton-Raphson conversions. And it is one of the best articles I have ever read about this specific topic. And so very quickly, is it working this time?
Even how long is this demo going to be?
Okay, very quickly. So this is just amplitude doing nothing with no input samples, and it was like that for like 5 minutes. You know, I like the idea of software binding. You know, it's like circuit bending, but with software. You change something in your code totally random, and you can get sounds like this, which is totally insane, just because of a minus sign or something like that. And I do that a lot in my own algorithms with fuzzers, audio algorithm, for example, or things like that. You just change a minus sign and you get horrible stuff like that. But it's so cool if you put that in the context of a song, for example. And it's unbelievable.
Cool, thank you very much again. Please give a big hand to Ivan Cohen.
No, thank you very much, everybody.